Hello students. So in our last lecture, that is lecture number 236 and 237, we have studied about interpolation. That means uh, how a function may be fitted to a set of tabulated values. A function is fit a function to a set of tabulated values. And we have discussed about two types of interpolation. One is linear interpolation, and another one is cubic interpolation. While doing this exercise, we assumed that these tabulated values, we assumed that they had no errors involved with them. However, if a tabulated values are obtained as a result of some experiments, there has to be some error. Now, these errors will vary over a range, and some errors may be quite large. In such a case, we can fit a curve only approximately with the aim of obtaining a curve which is statistically the best fit. Now, this is actually the buzzword, that is the best fit. It has to be a best fit. Now, suppose we have x1, x2, dot xn. These are the values of an independent variable, and correspondingly y1, y2, yn, these are the values of a dependent variable. So we have a function y, which is a y bar, I should say, is a function of fx, and we assume that this is an approximate function. Okay. Now there are errors associated with this proximate function. Suppose we assume that there is an error t1 which is associated with the function y1, the value y1 and the value y1 bar. So we can easily write the value of y1 as equal to fx1. Similarly, we can have an error associated with the second tabulated value y2 minus y2 bar. So this is y2 minus fx2, and so on. Dn value will be equal to yn minus yn bar, that is equal to yn minus fxn. So it is something like this. We have a function, say you have x values here, x1, x2 and x3, and corresponding, say you have, is that the y1 value, this is y1, this is y2, y3 and y4. So what we do, we make an approximate function fx. Now corresponding to x1, then we will have corresponding value y1 bar. Corresponding to x2, we will have a y2 bar. x3 will have y3 bar. But there is a slight difference between, so this value between y2 and y2 bar, this is d2, this is say d1, and so on and so forth. So these are the errors associated with the different y values. Now the function usually always, there has been always the main role or the main aim is to choose a function such that the d values are very close to 0 or very small. So we can have a minimization. So we can have a minimum of the all the error, that is all the di, it is equal to minimum of and so the difference can be both positive and negative. So we assume that it is a minimum of summation of the mod values, that is equal to the minimum of the summation of mod of I bar minus y I. Now maximum value of this error should be less than equal to value d, and minimum of di square will be equal to minimum of summation yi by minus yi whole square. These are called the metrics. Not a matrix, but a metric. METRIC. Metrics or distance functions, as they measure the distance. Near the distant function as measure the distance between the original value and the value corresponding to the function. Now this metric this metric this is immediately rejected as large deviations which are equal but of opposite signs. Since we are taking the deviations, they can be positive or negative, so that is why we are taking the mod values. That We're taking the deviations as a difference, not whether it is a positive value or a negative value. However, it is difficult to derive an analytical value, so that is why taking a square of the value is a good idea. That is why we are focusing on the square. Also, a function satisfying such a metric is called Chebyshev approximation. And if it satisfies this metric function, so that function will satisfy this is called Chebyshev. Chebyshev Chebyshev approximation. So, the advantage of using a minimum of t square, the Chebyshev approximation. The advantage of using this is the errors of opposite signs do not cancel out. Secondly, it weighs large errors more than small error. And the methods of calculus can be used analytically to derive the approximation. Calculus can be used, and if the deviations di, if these deviations have a normal or a Gaussian distribution, then the function fx, which is obtained by minimizing, can be shown to be the most likely one. So this is most desired value of di. Now the first approximation is called the least square fit. So least square fit, that is a problem of fitting a function fx to a tabulated value which minimizes the sum of the squares of the deviations. It's called fit. Now we consider the following table. If we have the following values of x and y arranged in this fashion, we have x and we have y. Say we have 1, 2, 3, 4, 5, 6, 7, and we have 1.2, 1.2, and then 2.1, then 2.8, then 2.7, then 4.5, then 5, and last 5.5. These are the values. So we plot x versus y. So we put x here, we put y here, and obtain a linear plot like this. So we write the equation as y1 is equal to a1 x plus a0. Now we have to we are now faced with picking the values of variables a0 and a, which will give us the best fit. Suppose the points are like this. We need to fit it with the best fit. So for that we have to use the error methods that we described recently. The next question we have to answer is whether we take the deviations between the tabulated values of y and those obtained from the straight line, or the tabulated values of x and those obtained from the straight line in the first case. So if we take the values of y and those obtained from the straight line, then we will have the following values. It is summation I 1 to n yi minus yi bar whole square is equal to n yi minus 2. We will use this form, so it will be a1 xi plus a0 whole square. Now in the second case, we assume that the straight line is represented by the equation x is equal to b1 y plus v0. That means the opposite one. We make the dependent and independent variables interchange. So the deviations would be I is equal to 1 to n xi minus xi bar whole square, which is equal to I is equal to 1 to n xi minus b1 yi plus b0 whole square. Now the straight lines obtained in these two cases are different. That means with y is equal to a1x plus a0 and x is equal to b1y plus a0. These two lines are different. Now so one is called the linear regression of y on x for the first case, for the y, linear regression of y on x, and the other one is called x on y. Now we need to minimize the values so to get the best fit. So the sum of the squares of the error, that means we write it as minimize the sum of squares of error measured values and that given. So it is given as minimum of S, that is minimum of 1 to n yi minus yi bar whole square, and it is equal to minimum of 1 to n, then yi minus a1 xi plus a0 whole square. Now this s is actually the function of these two unknown variables a0 and a1. So s is a function of a0 and a1. Just to minimize this, we need to take partial derivative. With respect to a0 and a1. So we need to write that del s by del a0, this is equal to and del s by del a1 is equal to 0. So in the first case, in this case, it will be summation I is equal to 1 to n 2 yi minus a1 xi minus a0 x, so minus a0 into minus 1 equal to 0. And for this case, it will be summation I is equal to 1 to n 2 yi minus a1 xi minus a0 into minus xi is equal to 0. So the first equation then becomes summation yi minus a1 summation xi minus na0 is equal to 0, and the second equation becomes minus summation xi yi plus a1 summation xi squared plus a0 summation xi is equal to 0. So rearranging the above equation, we get the following linear simultaneous equation for a0 and ai. It's called the linear simultaneous equation for a0 and a1. So these simultaneous equations are na0 plus summation xi into ai is equal to summation yi, and summation xi into a0 plus summation xi square into a1 is equal to summation xi yi, and ultimately we get the solutions. The solutions for a0 is equal to summation yi summation yi into summation a0 is equal to summation yi into summation xi square minus summation xi into summation xi yi divided by n into summation xi square minus summation xi square, and value for a1 will be equal to n into summation xi yi minus summation xi summation yi divided by n summation xi square minus summation xi whole square. So these are together. So these two are called the normal equations, and give the coefficients of the least linear square fit line, and they give coefficients of the linear least square fit line, or so called regression coefficients.